Problem 15.3. Draw the development of a lateral surface of the part P of the pentagonal prism as shown in the figure. Name the corners of the prism and the points at which the edges are cut. Draw the development assuming the prism to be whole. It is made up of 5 equal rectangles. Draw horizontal lines through points 1 dash, 2 dash, etc. to cut the lines for the corresponding edges in the development at points 1, 2, etc. Draw lines joining these points and complete the development as shown.
Development of surfaces. Problem 1522. Draw the development of the lateral surface of the truncated cone as shown in the figure. Assuming the cone to be whole, let us draw its development. First, draw the base circle in the top view and divide it into 12 equal parts. With any point O as center and radius equal to O'1' or O'7', draw an arc of the circle. The length of this arc should be equal to the circumference of the base circle. This can be determined in two ways. Calculate the subtended angle theta by the formula theta is equal to 360 degree into radius of the base circle upon slant height. Cut off the arc so that it subtends the angle theta at the center and divide it into 12 equal parts. Step off with a bow divider 12 equal divisions on the arc, each equal to one of the divisions of the base circle. Join the division points with O, thus completing the development of the whole cone with 12 generators as shown in it. The truncated portion of the cone may be deducted from this development by marking the positions of points at which generators are cut and then drawing a curve through them. For example, generators O'2' and O'12' in the front view are cut at points B' and B'1, which coincide with each other. The true length of the O'B' may be obtained by drawing a line through B' parallel to the base and cutting O'7' at B'. Then O'B' is the true length of O'B'. In last step, mark points B and B1 on generators O2 and O12 respectively, such that OB is equal to OB1 is equal to O'B'. Locate all points in the same way and draw a smooth curve through them. The figure enclosed this curve and the arc is the development of the truncated cone.
Hello friends. When two solids intersect or penetrate, their surfaces intersect at a common line of intersection. We must know the exact location of the intersecting line for the development of the solids. The line of intersection, also known as the transition line. It could be of any shape. It would be a straight line when solids having flat surfaces intersect. The line could be a curved line when solids having curved surfaces intersect. Or it could be a combination of straight and curved lines when one of the intersecting solids is flat and the other one is curved. How can we obtain the two representation of the line of intersection? For that, first identify key points on the surfaces of the intersecting solids. Then, draw a number of lines known as generators from key points to plot the line of intersection.
Intersection of cylinder and cylinder. Problem 16.8. A vertical cylinder of 80 mm diameter is completely penetrated by another cylinder of 60 mm diameter, their axes bisecting each other at right angles. Draw their projections showing the curves of penetration, assuming the axis of the penetrating cylinder to be parallel to the VP. Draw the front view and the top view and show lines for 12 generators in the horizontal cylinder in both views. Line method. Mark points P1, P2, etc. at which lines 1, 1, 2, 2, etc. intersect the circle, showing the surface of the vertical cylinder in the top view, and project them to P-1, P-2, etc. on corresponding lines 1, 1, 2, 2, etc. in the front view. Draw the required curves on both sides of the axis through points thus located. Hidden portions of the curves coincide with the visible portions. Points P-1, P-4, P-7 and P-10 are the key points where the curves change direction. Cutting plane method. It will be seen that in this problem there is practically no difference between the line method and the cutting plane method. But the latter method proves more useful in solving problems in which none of the projections show a line view of the surface of a solid. Assume a series of horizontal cutting planes passing through the lines on the horizontal cylinder and cutting both the cylinders. Sections of the horizontal cylinder will be rectangles, while those of the vertical cylinder will always be circles of the same diameter as its own. Points at which sides of the rectangles intersect the circle will lie on the curve of intersection. For example, let a horizontal section plane through points 2 and 12. In the front view, it will be seen as a line coinciding with the line 2 2 The section of the horizontal cylinder will be a rectangle of width W, that is the line 212. The section of the vertical cylinder will be a circle. Points P2 and P12 at which the sides 2, 2 and 12, 12 of the rectangle cut the circle lie on the curve. These points are first marked in the top view and then projected to the points P-2 and P-12 on the lines 2 2 and 12 12 in the front view. Points on the other side of the vertical axis are located in the same manner. Intersection of cone and cylinder. Problem 16.22. A vertical cone diameter of base 75 mm and axis 100 mm long is completely penetrated by a cylinder of 45 mm diameter. The axis of the cylinder is parallel to the HP and the VP and intersects the axis of the cone at a point 28 mm above the base. Draw the projections of the solids showing curves of intersection. Cutting plane method. Draw lines dividing the surface of the cylinder into 12 equal parts. Assume a horizontal cutting plane passing through, say, point 2. The section of the cylinder will be a rectangle of width W, while that of the cone will be a circle of diameter EE. These two sections intersect at points P2 and P12. These sections are clearly indicated in the top view by the rectangle 2, 2, 12, 12 and the circle of diameter EE. In the front view, the cutting plane is seen as a line coinciding with 2 2 Points P2 and P12 when projected on line 2 2 with which the line 12 12 coincides will give a point P-2 with which P-12 will coincide. Then P-2 and P-12 are the points on the curve of intersection. To obtain the points systematically, draw the circles with center O and diameters DD, EE, FF, etc., cutting the lines through 1, 2 and 12, 3 and 11, etc. at points P1, P2 and P12, P3 and P11, etc. Project these points to the corresponding lines in the front view. Two more key points at which the curve changes directions must also be located. Their positions are determined from the side view. They are the points of nearest approach, that is M double dash and N double dash, at which the lines drawn from the center of the circle and perpendicular to the extreme generators of the cone cut the circle. Project these points to M dash and N dash in the front view and to M and N in the top view on the corresponding lines. Draw curves through these points in both the views. The back curve in the front view will coincide with the front curve. In the top view, a part of the curve will lie hidden and hence it will be dotted. Draw similar curves on the right hand side of the axis of the cone. Isometric projection. Introduction. Isometric projection is a type of pictorial projection in which the three dimensions of a solid are not only shown in one view but their actual sizes can be measured directly from it. If a cube is placed on one of its corners on the ground HP with a solid diagonal EC perpendicular to the VP, the front view is the isometric projection of the cube. The three lines CB, CD and CG meeting at C and representing the three edges of the solid right angle are also equally inclined to the VP and are therefore equally foreshortened. The diagonal BD of top face is parallel to the VP and hence retains its true length. The lines parallel to these axes are called isometric lines. that is lines BF, DH, AE, FG, AD, EH, GH, AB and FE are called isometric lines. BF, DH and AE lines are parallel to axis CG. FG, AD and EH lines are parallel to axis BC. GH, AB and FE lines are parallel to axis CD. The 6 faces of the cubes are called isometric planes. These faces are seen as rhombus. The axes CB, CD and CG make equal angle of 120 degrees with each other. In isometric, the vertical line remains vertical and horizontal lines make angle of 30 degrees with horizontal as line CG remains vertical but lines CB and CD make 30 degrees angle each with horizontal. To find isometric scale, construct a square BQDP around diagonal BD. Then BP shows true length of side BA. Side BP makes 45 degrees angle with diagonal BP. In triangle ABO, BA upon BO equals 1 upon cos 30 degrees is equal to 2 upon root 3. In triangle PBO, BP upon BO equals 1 upon cos 45 degrees which equals root 2 upon 1. Now, BA upon BP equals 2 upon root 3 into 1 upon root 2 which equals root 3 upon root 2 which equals 0.815. Therefore, BA equals 0.815 into BP. That means isometric length equals 0.815 into true length. Isometric drawing of planes or plane figures. Problem 17.1. The front view of a square is given in figure. Draw its isometric view. As the front view is a square, the surface of the square is vertical. In isometric view, vertical lines will be drawn vertical while horizontal lines will be drawn inclined at 30 degrees to the horizontal. Through any point D, draw a vertical line DA equals DA. Again, through D, draw a line DC equals DC inclined at 30 degrees to the horizontal and at 60 degrees to DA. Complete the rhombus ABCD, which is the required isometric view. The view can also be drawn in direction of the other sloping axis as shown in the figure. Problem 17.2. If the given view is a top view of a square, draw its isometric view. As the top view is a square, the surface of the square is horizontal. In isometric view, all the sides will be drawn inclined at 30 degrees to the horizontal. From any point D, draw two lines DA and DC inclined at 30 degrees to the horizontal and making 120 degrees angle between themselves. Complete the rhombus ABCD, which is the required isometric view. Isometric projections. Problem 17.7. The figure shows the front view of a circle whose surface is parallel to the VP. Draw the isometric view of the circle. Method of points. Enclose the circle in a square, touching it in points 1, 2, 3 and 4. Draw the diagonals of the square cutting the circle in points 5, 6, 7 and 8. Draw the isometric view of the square and on it mark the midpoints 1, 2, 3 and 4 of its sides. Obtain points 5, 6, 7 and 8 on the diagonals as explained in the previous problem. Or after determining the position of one point, draw through it lines parallel to the sides of the rhombus and obtain the other 3 points. Draw a neat and smooth curve passing through the 8 points, that is 1, 6, 2, 7, etc. The curve is the required isometric view. It is an ellipse. Problem 17.16. Draw the isometric view of the frustum of the hexagonal pyramid as shown in the figure. Enclose the front view and the top view in rectangles. Draw the isometric view of the rectangular box. Locate the 6 points of the base of the frustum on the sides of the bottom of the box. The upper 6 points on the top surface of the box are located by drawing isometric lines. For example, P1 and Q1 intersecting at a point 1. Join the corners and complete the isometric view as shown. Problem 17.17. Draw the isometric view of the pentagonal pyramid, the projections of which are given in the figure. Enclose the base in the top view in an oblong. Draw an offset OQ, that is PQ, on the line AB. Draw the isometric view of the oblong and locate the corners of the base in it. Mark a point Q on the line AB such that AQ equals AQ. From Q, draw a line QP equal to QO and parallel to 2C. At P, draw a vertical OP equal to O'P'. Join O with the corners of the base, thus completing the isometric view of the pyramid. The figure shows the isometric view of the same pyramid with its axis in horizontal position. Oblique projection. Oblique drawing of prism. Problem 18.4. A hexagonal prism, base 50 mm side and axis 100 mm long, resting on its base on HP, is cut by a section plane perpendicular to VP and makes an angle of 45 degrees with the HP. It passes through a point on the axis 20 mm from its top. Draw the oblique projection of the prism by the Cavalier method with receding axis inclined at 45 degrees with the horizontal when A. Two rectangular faces of the prism are equally inclined with VP and B. one rectangular face of the prism is parallel to VP. Draw the front view and top view of the hexagonal prism as shown in the figures. Enclose the top view in rectangular box. Draw oblique projection as shown in the figures using box method as explained in problem 17.14, problem 17.15 and problem 17.16. Similarly, using the box method, draw sectional oblique projection as shown. Perspective projection. Introduction. Perspective projection or perspective drawing is the representation of an object on a plane surface called the picture plane as it would appear to the eye when viewed from a fixed position. Principle of perspective projection. In perspective projection, the eye is assumed to be situated at a definite position relative to the object. The vertical plane, which in perspective is called a picture plane, is placed between the object and the eye. Visual rays from the eye to the object converge to a point in the eye and are therefore inclined to the picture plane. The rays pierce the picture plane and form an image on it. This image is the perspective of the object. Definitions of perspective elements. Various elements used in obtaining the perspective views are defined as follows. Ground plane GP. It is a horizontal plane on which the object is assumed to be situated. Station point S. It is the point where the eye of the observer is located while viewing the object. Picture plane PP. It is a vertical transparent plane located between the station point and the object which is to be viewed. It is the plane on which the perspective is formed. The front view of perspective elements and of the object, if necessary, is also projected on this plane. Horizontal plane HP. This imaginary plane is at the level of the eye, that is the station point. It is a horizontal plane above the ground plane and at right angles to the picture plane. Auxiliary ground plane AGP. It is a horizontal plane placed above the horizon plane. The top view of the object and of the perspective elements is projected on this plane. Ground line GL. The line of intersection of the picture plane with the ground plane is called the ground line. Horizon line HL. It is the line in which the horizon plane intersects the picture plane. It is parallel to the ground line. Perpendicular axis PA. It is the line drawn through the station point perpendicular to the picture plane. It is sometimes called the line of sight or axis of vision. Center of vision C. The point in which the perpendicular axis pierces the picture plane is called the center of vision. It lies on the horizon line. Central plane CP. It is an imaginary vertical plane which passes through the station point and the center of vision. It contains the perpendicular axis. It is perpendicular to both the picture plane and the ground plane. Parallel perspective or one-point perspective. When an object has its one or more faces parallel to the picture plane, its perspective is called a parallel perspective and also called one-point perspective, as the edges converge to a single vanishing point of the parallel faces. The given figure shows the perspective view of a hut having its front face in the picture plane. The front face is seen in its true size and shape, while the back parallel face is of the same shape but reduced in size. As the lines AF, BG, CH, DJ and EK are perpendicular to the picture plane, their perspectives A', F', B', G', etc. converge to the center of vision C' on HL. Note that vertical lines AE, CD, etc. remain vertical in perspective. Similarly, horizontal lines ED and KJ and sloping lines AB, BC, FG and GH, which are all parallel to the picture plane, remain respectively horizontal and sloping in perspective. Angular perspective or two-point perspective. When an object has its two faces inclined to the picture plane, its perspective is called angular perspective, also called two-point perspective, as the edges of the object converge to two vanishing points. Problem 19.4. A rectangular block 30 mm into 20 mm into 15 mm is lying on the ground plane on one of its largest faces. A vertical edge is in the picture plane and the longer face containing that edge makes an angle of 30 degrees with the picture plane. The station point is 50 mm in front of the picture plane, 30 mm above the ground plane, and lies in a central plane which passes through the center of the block. Draw the perspective view of the block. Draw the top view ABCD with A in PP and the longer edge AB inclined at 30 degrees to PP. Mark its center O. Mark S, the top view of the station point, on a vertical line through O and 50 mm below PP. Draw lines joining S with the corners B, C and D and intersecting PP at points B1, C1 and D1. Draw the ground line GL at any distance between PP and the horizon line HL 30 mm above GL. Through S, draw lines parallel to AD and AB, cutting PP at points V1 and V2 respectively. Project V1 to V1 and V2 to V2 on HL. V1 and V2 are the vanishing points. Perspectives of edges AD, EH, BC and FG will converge to V1 and those of edges AB, CD, EF and GH will converge to V2. Perspectives of vertical edges AE, BF, CG and DH will remain vertical. As AE is in the picture plane, its perspective will be equal to the true length and the end E will lie on GL. Therefore, through A, draw a vertical line to a point E' on GL and on it mark A' so that A', E' equals AE. This length may be measured directly or may be projected from the front view as shown. Draw lines joining A' and E' with V1 and V2. Through B1, draw a vertical line to intersect A' V2 at B' and E' V2 at F'. Similarly, draw a vertical through D1 and obtain points D' and H'. Draw lines joining B' and F' with V1 and D' and H' with V2, intersecting at points C' and G' respectively. They must lie on the vertical line through C1. Note that lines meeting at G' are all hidden and therefore are shown dotted. Oblique perspective or three-point perspective. When an object has its three faces inclined to the picture plane, its perspective is called oblique perspective and is also called three-point perspective as the edges of the object converge to three vanishing points as shown in the figure. Problem 19.5. Draw the perspective view of a cube of 80 mm side having its one corner of the edge on the ground plane and the other corner of the edge resting on the picture plane such that the edge is inclined at 30 degrees to the picture plane. The other two edges of the corner are equally inclined with the picture plane. The station point is 100 mm in front of the picture plane, 150 mm above the ground plane, and lies in a central plane which passes through the center of the cube. Draw projection plane lines PP and PPE perpendicular to each other. Draw side view on PPE from auxiliary top view. Draw top view on PP by taking projection from side view. Mark the station point S for FV and S1 for SV at a distance of 100 mm from PP and PPE respectively and 150 mm from GL. Obtain the three vanishing points V1, V2 and V3 and complete the perspective view as shown. Problem 20.8. A pictorial view of bearing block is shown in the figure. Draw the front view, left-hand side view and top view according to the first angle projection method. The procedure of preparing the orthographic views is illustrated in the following steps. Step 1. take a half imperial size drawing paper of 560 mm into 380 mm. Draw the border lines taking A equals 30 mm and B equals 10 mm as shown in the figure. Now, the clear space in the drawing paper is 520 mm into 360 mm. The scale of drawing is decided from the size of object and number of views required to draw. Let L, W and H be the length, width and height of the object respectively. The spacing between two views can be calculated as shown in the table. If these distances E and F are less than 20 mm, adopt the suitable standard scale. In the above illustrated problem, E and F are 95 mm and 75 mm respectively. Select suitable scale and draw required blocks depending upon the number of views. Step 2. Mark centers for circle. Draw center lines passing through these circles and extend in other views also. Step 3. Draw circle of required diameter in the front view as well as the top view. Draw the other lines in the front view and project them in the side view as well as in the top view. Erase construction lines. Step 4. Clean the drawing paper. Fair first circles. Complete the views by fairing various lines. The thickness of the different types of lines should be as suggested in the figure as per the given tables. The lines should be clean, dense and uniform. Draw extension lines. Draw dimension lines. Insert dimensions. Observe that the height of the numerals should not be more than 3 mm. It should be written freehand. Aligned method of writing dimensions is recommended. Follow IS 11669 1986 for dimensioning. Complete title block by specifying unit of dimensions, symbol of method of projection and scale adopted. Fair boundary lines by 2H pencil. Centers of gravity and moments of inertia of areas. Illustrated problems on center of gravity. Problem 21.3. Find graphically the center of gravity of the I section as shown in the figure. As the section is symmetrical above its vertical axis y dash, the center of gravity must lie on that axis. Draw the given section to a convenient scale. Divide it into three rectangles 1, 2 and 3 and locate their centers of gravity G1, G2 and G3 respectively at the points of intersection of their respective diagonals. Through these points, draw parallel lines of action of forces representing the area of each rectangle. These lines may be drawn in any direction except vertical, as the center of gravity lies in the vertical axis. Name these forces as AB, BC and CD respectively according to Bose notation. This figure is also called the space diagram. Calculate the areas of the rectangles 1, 2 and 3. They will be 6000, 4000 and 2000 square mm respectively. Draw a line parallel to the lines of action of forces and on it mark a point A. Select any convenient scale, say 1 cm equals 1000 square mm, and cut off lengths AB equals 6 cm, BC equals 4 cm and CD equals 2 cm in the direction of the forces. The line AD is also called the load line or force diagram. Mark a point O at any convenient position either above or below the line AD and draw lines AO, BO, CO and DO. The point O is called the pole and the whole figure is called the polar diagram. Mark any point A dash on the line of action of the force AB and draw a line parallel to AO. Through the same point, draw a line parallel to BO to intersect the line of action of the force BC at a point B dash. Through B dash, draw a line parallel to CO to intersect the line of action of the force CD at a point C dash. Through C dash, draw a line parallel to DO to intersect the line drawn parallel to AO at a point D dash. Through D dash, draw a line parallel to the lines of action to intersect the axis Y dash at a point G. This line is the line of action of the resultant R of the forces and G is the center of gravity of the section. Figure A dash, B dash, C dash, D dash is called the funicular polygon or link polygon. Illustrative problems on moments of inertia. Problem 21.11. Find graphically the moment of inertia of the rectangular section 10 cm wide into 20 cm deep as shown in the figure about the axis y dash passing through its center of gravity. Draw the given rectangle to a suitable scale. Say 1 cm equals 2 cm and draw the axis y dash passing through its center of gravity. Divide the rectangle into a number of equal strips, say 8, parallel to the axis. Draw lines of action of forces representing the area of each strip parallel to the axis and passing through the respective centers of gravity of the strips. This is the space diagram. Calculate the area of each strip. Select a convenient scale, say 1 cm equals 20 square centimeters and draw a load line AK as explained in the previous problem. Lengths AB, BC, etc. will each be equal to 1.25 centimeters each. Mark the pole O at any convenient polar distance D1, say 5 centimeters from the line AK and complete the polar diagram P1 by joining O with the points A, B, so on up to K. Draw the funicular polygon F1 as explained in the previous problem. Produce all the sides of the polygon to intersect the axis at points A1, B1, so on up to K1. Note that in this problem, points A1, B1, C1 and D1 coincide with points K1, H1, G1 and F1 respectively. Measure the intercepts A1, B1, B1, C1, etc. Assuming these intercepts to be forces and selecting a convenient scale, say 1 centimeter equals 0.333 centimeters, draw the second load line. While drawing this line, it should be noted that the intercepts for the strips on one side of the axis should be drawn in one direction, while those for the strips on the other side of the axis should be drawn in the opposite direction. Thus, the intercepts from A-1 to E-1 coincide with those from K-1 to E-1. Note that according to the selected scale, length A-1 E-1 is 3 times the length A1 E1. Select a pole O1 at a suitable distance D2, say 6 centimeters, and complete the polar diagram P2. Draw the corresponding funicular polygon F2. The intercept A2K2 of this polygon on the axis YY' is the moment of inertia of the rectangle about the axis YY' to the moment scale, which is determined as shown. If the scale of the space diagram is 1 centimeter equals n centimeters, and if the area scale for the first load line is 1 centimeter equals n1 centimeter square, and if the intercepts from the funicular polygon F1 are represented on the second load line to the scale 1 centimeter equals n2 centimeters, and if the polar distances in polar diagrams P1 and P2 are d1 centimeters and d2 centimeters respectively, then the moment scale equals n square into n1 into n2 into d1 into d2, which equals 2 square into 20 into 0.333 into 5 into 6, which is equal to 800 centimeters raised to 4. The length of the intercept A2K2 is 8.4 centimeters. The moment of inertia equals length of the intercept A2K2 in centimeters into the moment scale, which equals 8.4 into 800, which equals 6720 centimeters raised to 4.